particles at each other, something happens, and then you measure some final state. You need a framework in which to analyze these and understand them. And that framework is provided by S-matrix theory. And S-matrix theory, as we've discussed, has three essential ingredients: analyticity, crossing, and unitarity. And they're based on very basic properties. Unitarity is the conservation of probability. Crossing is about the fact that the processes are relativistic, and analyticity is a consequence of causality. Now, one important ingredient that illustrates how important crossing is and analyticity is what I want to discuss now in the first. This talk is going to be on the blackboard like the others, but then the second part I'm going to do slightly more like a seminar to pull various things together. So now what we've learned is that there are these three scattering regions which are related in 2-to-2 scattering by crossing symmetry. And what I've illustrated here in the T-channel is that there are resonances, let's say, and there are resonances similarly in the other channels. Now, crossing symmetry relates those to each other. And the question is, how can you understand how they're connected? And a way to see that is to discuss something called Reggi theory, named after the Italian Tullio Reggi. So let me very quickly, and it's going to be only a quick sketch of what Reggi theory is about, to try to explain what it does. And what is rather, well, let's first begin with something that we already met before, which is partial wave amplitudes. Partial wave amplitudes are where you take an amplitude and you decompose it into its components that have particular angular momentum. And we're going to do that in the T channel rather than the S channel. It's just convenient to do that. So just like we had the other day, we're going to write the amplitude as a function of T and a function of cos theta, but now it's cos theta in the T channel, so that's why I put a little sub T to remind you. And that's equal to 16 pi, that's just for convenience, a sum over L, and this time I'm going to write the L as a capital L to emphasize it's an integer. Okay, so this is going to be 2L plus 1, the partial wave amplitudes, and then the Legendre polynomials, assuming that the process is spinless. Okay. And what we learn is that these partial wave amplitudes contain poles in them which correspond to the resonances of the different spins. So let's make a little plot of the simplest, the ones that we find most easily, which is to plot their mass squared against their angular momentum. So here is angular momentum. So here is L, 3, and in fact, I'll show you some plots later. So we have mass here, if I've drawn this correctly, something like this, and which I haven't, so maybe I should have drawn the line first and then put the points on. So here we have, for example, the rho, and here we have the F2, and here we have the rho 3, and so on. And here we have another line which is almost parallel to it, which has a K star, and then it has a K2 star in the strange channel, and these are all supposed to be at the same. So if we happen to make a plot of against mass squared of the states, what we see is that they lie along some line, which in fact turns out to be rather close to a straight line. We're going to concentrate on the top one, the one which has the states made out of non-strange quarks. And what we see is that we're going to call this is equal to T. This is the mass squared at which these objects happen. And so you can think of this line as a function of t. And we call it alpha of t, and it's approximately, for the row trajectory, it's called a trajectory. Why it's called a trajectory we'll see in a minute. If these are connected, in which this is roughly 0.5 plus alpha primed times t, where alpha primed is about 0.9 GV to the minus 2. So it happens that if you just draw that line, where that line crosses the integers at 1, 2, 3, 4, and so on up to 5, there are the masses of the particles. Now, that's just a game that you could play, and you may think, oh, it's just an accident. Well, it turns out that it isn't, and we'll see that it actually makes sense to ask what happens if the angular momentum is not only not equal to an integer, but equal to some other number, some number in between the integers, and even to take the number L to be complex. That's rather amazing that that happens. So let's see why. What we just learned from here is that these partial wave amplitudes have a pole, and the L equals 1, 1 has a pole at m rho squared, and the L equals 2 has it at f2 squared, and the other one, the next one at 3 at m rho 3 squared. So we learn that the FL of t's from phenomenology has some pole at some mass, which is related to the mass of the resonance minus t. And this corresponds, just because it's a linear function, to be where L minus alpha of t. So all you do is you change t to alpha of t using that equation there. And so this has a pole. It says it has a pole at the L equals 1, 1 has a pole where at the value of t at which this function alpha of t is equal to 1. Okay. Now, Reggie had the idea, but he did this not in relativistic processes, he'd studied it in potential scattering, of saying, let's consider this, as I said, if L is not an integer, so does it make any sense when the angular momentum is equal to 1.36? What does that mean? And then he had an even crazier idea, let's make it complex. So, to understand how that tells you something, let's make L complex. Okay, and so as to distinguish the integers from the complex values, that's why I call the integers capital L. So now let's look, and maybe it's not obvious why, but we'll see in a minute. Consider the complex L plane. So this is the complex L plane, and here are the integers going along here, obviously 0, 1, 2, 3, 4, and so on. And we're going to consider an integral that goes up the line here at -1/2. Why it's at -1/2, we'll see. And we close it at infinity. Okay. So imagine we're going to consider such an integral. And we're going to consider an integral of a particular function. So I can write that here. So we have enough space. We consider an integral which is again a function of these variables, t and zt, which is going to be the integral round the contour dl 2l plus 1 f of l and t divided by sine pi l Legendre polynomials pl of minus zt. So we're going to consider the Legendre functions with L also complex. And this is an integral round a contour. Now you may see that there is some sort of connection between those two, but it may be not yet obvious what the connection is. And this contour goes this way round, which is slightly unusual because it goes up this axis. Okay, it goes clockwise rather than anti-clockwise. So let's do this integral. We can do this integral in two ways. One, we can do the integral up this line, and then the integral that's supposed to be at infinity. And the integral at infinity, we assume that the properties of these functions are that it's equal to 0. So at infinity it's equal to 0. So the integral is really only the integral up that line. Okay. So this is equal to the integral, and why it's this funny line, minus a half minus I infinity minus a half plus I infinity. And maybe we don't need, well, I'll write it small here, but it's just the same thing. Obviously I haven't done anything. And the integral, you may want to write down at infinity, is assumed to be equal to 0. Now, how else can we evaluate this integral? A way we know how to integrate round a contour is it's equal to 2 pi I times the sum of the residues of any poles inside. Now, what poles of this function are included inside the contour? Because I've written this factor sine pi L, that's equal to 0 every time L is an integer. So what it's going to do is there's going to be 2 pi I times the residue of every one of those poles. And it's going to be a sum of them. In fact, it's going to reproduce exactly that sum, other than a sums factor. But then there can also be other poles, those we've put in by hand, the sine pi L's, but it can be that this function has poles. Indeed, our model, I have to write it over here because otherwise we knew that when L was an integer, that these partial wave amplitudes, FL of t, behaved like L minus alpha t. So these have poles as well. Let's imagine there is a pole here, which is the pole in the function f, okay, as opposed to the ones we've put in by hand. So now let's write what that answer is. And if I do it here, we see that it's equal to, we've gone the wrong way round the circle, so it's minus 2 pi I times the sum over the integers of 2L plus 1 F L of t PL of minus z, or minus z, which is, we've got a pole every time L is equal to an integer, and we have to write down what the residues are. So what is the residue of, I don't have enough space here, so what is the residue of sine pi L? Well, the residue is multiply where the pole is, L equal L minus L, and take the limit in which little l goes to capital L, right? And you remember you use some rule named after a French mathematician, de L'Hopital, who says you take the derivative of the top and the bottom with respect to L, and so the top is 1, and at the bottom one it's pi times cos pi L, and that's equal, when L is equal to an integer, to minus 1 to the L over pi. Okay, because cos pi of an integer is minus 1 to the L. So, the answer is minus 1 to the L divided by pi. And that's what it is for an integer. And then there is another piece which comes from however many of these poles there are, which are the poles in this function here, as opposed to the poles in the sine pi l. This only has poles for integer values. So let's add that bit. And again, let's just assume for the minute there's just one of these poles. And it will be, the pole is at L, I wrote it over here, the pole will be at L equals alpha of t. So this is the pole at the position L equals alpha of t. Okay, it moves with the kinematic variable, and so it will be 2 alpha plus 1. The residue of the pole, which is usually written as beta, divided by sine pi alpha of t, p alpha of t of minus zt, or zt. And I've just assumed there is one of these poles, okay? You can imagine that if there are several of them, you have to add up all of those. And these are called regipoles. So these is the sum over regipoles. And in potential scattering, Reggie found that depending on the potential, there were indeed these poles. That's just a curiosity. Now, let's go back here to, L equals 0 to infinity. So that was the sum, so the capital L. Now, the only thing you have to notice here is that minus 1 to the L, when L is an integer, which is in this sum, the Legendre polynomials are odd under L goes to Z goes to minus Z if L is odd. So in fact, they have the property that PL of minus Z is equal to minus 1 to the L times PL of Z when L equals an integer. So that was the reason for writing minus Z here, was so that it actually reproduces exactly the piece that we wanted there. Okay, so this minus 1 to the PL of minus Z is just PL of Z. So this equals, doesn't go across that line, this equals that. So now we can collect the pieces together, and we see that up to a minus sign, and you take the answer and multiply by 8i, so you take the answer and you multiply by 8i, and then that will reproduce a 16 pi, which is what we want here. We have that f of t and zt, which is by definition this, is equal to, and we put these pole terms on the other side of the equation, minus 16 pi, minus sign doesn't matter, to alpha plus 1, beta of t, which come from the regipoles, sine pi alpha of t, p alpha of t of minus zt, plus this integral, so 8i times the integral from minus a half plus I infinity to minus a half plus I infinity dl 2l plus 1 fl of t sine pi l of t sine pi l pl of minus zt. So when we've done the integral, the sum of the partial waves can be written as a sum, and in general there will be more than one, and I've just drawn one term, a sum of regipoles, a piece that comes from regipoles, plus an integral that goes up that line. And this integral is called the background integral. The background integral. Why it's there, we'll see in a minute. So we've taken our partial wave series and rewritten it in a rather different way in terms of something which are sums of regipoles plus a background integral. And these regipoles, well, they may or may not exist, but it turns out they do. Now, when is this useful? Let's remove all of that. And let me stress here, I've just put one regipole. There would be, in general, a sum over regipoles. Yes?
Is this a way to divide resonant and non-resonant part of
No. We will, there is a way to do that, but it's not yet. It's buried in there, okay, but not yet divided. Because this piece, this piece can include resonances and non-resonances in the regipoles, if that's what your question. You will see. It doesn't contain resonance. That is correct. But this bit still does. You'll see in a minute how they separate. Now, let me remind you what ZT is. If the process is AA to AA, whatever your favorite particles are, with mass m, all having mass, the same mass, then cos theta in the T channel is 1 plus 2s over T minus 4m squared. Now, let's do something completely crazy. Let's take s to infinity. We started from a partial wave expansion, which is valid inside this region here. Okay? In fact, it only converges in general inside that region. Now we rewrite it in terms of something called regipoles plus a background integral, and now magically, at some fixed value of t is just a constant, it's a constant variable, we're going to take along some line with t fixed, s going to infinity. Why would we want to do that? Well, clearly s goes to infinity is only physical if I'm inside the s-channel physical region. So I've got to change t from the values in which it was in this physical region to the ones inside this physical region to make any connection. Here t is negative, here t is bigger than 4m squared. But let's do that. Why do we want to do that? Because something simple happens. Legendre functions are polynomial. When the L is an integer, they're polynomials. So when z goes to infinity, or z goes to infinity, Pl of z is a polynomial of order L. It behaves like z to the power L. Now, miraculously, that still holds if L is not an integer and is even a complex number. So you can show that Pl of z, when z goes to infinity, behaves like actually two pieces. A piece that behaves like z to the L, and another piece which behaves like z to the minus L minus 1. Now clearly when L is an integer, these pieces aren't there, but when L is not an integer, they do appear there. Now, what do you notice about these two numbers? This one wins, is the biggest one, if the real part of L is bigger than minus a half, and if the real part is less than minus a half, this one wins. So that's the reason that this integral runs up the line minus a half. It divides the world into two pieces like that. So if this regipole here is to this side, as I've drawn it, when S goes to infinity, namely ZT goes to infinity, it's going to be one of these terms that's going to control the high energy behavior of the amplitude. And so this tells us that F of T and ZT, when ZT goes to infinity, behaves like the minus sign doesn't matter and we can absorb it into there. So let me call it some beta bar of T, which absorbs all the unnecessary constants, P alpha of T. And then the Legendre function like that. And so the high energy behavior of the amplitude is given by the behavior of the rightmost regipole. Now, Reggie did this in potential scattering, where there is no relationship between one channel and another. But here we're doing it in a relativistic process, where taking S to infinity, provided we go and change T from being in the T channel to T being here negative, it tells you what the high energy behavior of the amplitude is along here. And it says the piece that dominates is the piece with the angular momentum continued from values which once were integers, and they're integers when T is equal to m rho squared, m whatever squared, to a region when T is negative. A miracle happens. Take your straight line that's here and imagine continuing it into the T negative region. Look at the high energy behavior of the scattering amplitudes along this line here, along any of these fixed lines where T is negative, and determine what this power is, because this is the same as, well, in fact, up to constants, is S to some power where that power is related to the Reggie trajectory. And what do you find? It's exactly the continuation of that line. So what is it telling us? It's telling us this goes back to Angela's question, or it's related to it. We had an amplitude, naively. Well, maybe I have to do something else first. Before explaining that, let me do something else. The high energy behavior here, you can think of as being generated by particles being exchanged in the cross channel. So the high energy behavior of this process is controlled by what happens in what you can exchange in the T channel. Now, if you were doing this naively, you'd say, well, the particles I can exchange in this channel are each of these resonances, the things that appear in that channel, the rho or whatever the quantum numbers are, a resonance, an object with spin 1, an object with spin 2, an object with spin 3, and I have to add them all up. Well, what Reggie tells you is, the way to add them all up is they all have some complex angular momentum, and it's the continuation of that complex angular momentum into this kinematic region that actually does the sum for you. So the sum of all of these elementary particle exchanges is all encapsulated in one regipole. So, those words mean that a regipole encapsulates, or sum encapsulates, an infinite sum of elementary particle exchanges. With integer spins, and in fact even with half-integer spins if you include fermions as well. So a regipole with complex angular momentum complex L. That's sort of amazing. And it's that's the basis of string theory. String theory automatically has that property. The original hadronic string had that property built into it.
Sorry, but in potential scattering, how would you say this thing?
It's something completely different. There isn't a way to say it. It's physically it doesn't exist. But nevertheless, in potential scattering, by studying potential scattering, Reggie discovered that there were these poles in the complex angular momentum plane. But it's really only a relativistic theory that you see that they have this remarkable property. So, let us consider the cross-section for some process. Consider a process which, maybe I should write the process first. If we consider this process, I don't want to take too long, otherwise I can't do the next bit. But if you consider this process, it's a process in which there are baryon resonances. So if you draw what the cross-section is as a function of energy in the S channel now, you will have a sequence of resonances. Now what Reggie theory says is that the high energy behavior of this process, I haven't drawn that very well, so let me draw it again. And then it becomes smooth. And what Reggie theory says is this high energy behavior, instead of thinking about it as a large sum of resonances, you can think of it as some particle being exchanged in the chi channel, which has a spin which is not an integer, and that process is an exchange in this channel, so now it's a proton and a neutron, a pi minus and a pi zero, which has the quantum numbers of the rho. And that's just the continuation of this trajectory which had the rho on when there were physical values, but now it's continued into this region. And so this gives you a behavior of s to the alpha rho of t, where that's the trajectory on which the rho lies. So that this is this s to the alpha rho of t. I haven't specified very well what I've actually plotted. And now a remarkable thing happens, an even more remarkable thing happens, which is that the high energy behavior isn't arrived at randomly. It turns out that it's the average of what happens already at low energies. That's a bit amazing. So the low energy behavior and the high energy behavior are connected with each other. And what it tells you, and what is embodied in the hadronic string theory, is exactly that property. So let us give you an example. In this process, at low energies, you might have thought, oh, we'll sum over resonances. There are many of them. Okay, many of them, and they're baryons. So this is pi n, let's say to pi n. So there's the process in the low energy region. It's a sum over resonances. And as you go up in energy, you'd have to have more and more resonances adding together. But they all overlap with each other, and they give something smooth. And this is equal to the sum of Reggie poles, what you exchange in the cross channel. Here we've got an example in which there's essentially just one Reggie pole, the rho. Now what is interesting about this, as I said, this is automatically encapsulated in string theory, and you'll see why it's a string in a minute, or see whether it's related to a string, if we draw quark line diagrams. So if we draw a line for each quark, then this process, you can think of like that. There's a meson coming in, the quark and an anti-quark between the initial state annihilate, and then they're produced again. And in the middle, there are baryon resonances, something with 3 quarks. You sum up a large number of those, and it's equal to the exchange of a meson in that channel. And string theory automatically has that property built into it, because you think of these as like rubber sheets, and when you pull the sheet this way, then it contracts in this direction. So you start with a sheet that looks like this, completely symmetric, and you pull the ends this way, and then you see there are baryon resonances, and if you pull it this way, you see that they're meson regipoles. And what is interesting about this is that it's unlike Feynman amplitudes, because in Feynman amplitudes, you add S-channel exchanges and T-channel exchanges and U-channel exchanges to each other. Here it says the infinite sum of all the S-channel resonances is equal to the infinite sum of the T-channel exchanges. You don't add them to each other, they're related to each other, and that's this property that this averages exactly what is going on here. Now, I just want to take a couple more minutes and we'll get to Angela's question. The particular reason for taking this process, pi minus p goes to pi 0 n, rather than pi minus p goes to pi minus p, is because, as you see, charge is being exchanged in this channel, and so that tells us that the quantum numbers are not the quantum numbers of the vacuum. Okay, this object, the rho, has got to have charge plus or minus 1, depending on which direction you want. But what happens if you... maybe I don't want to erase that, so let me go here. Let's consider k plus p goes to k plus p. The particular process here, in terms of quarks, is that there are no quarks that can annihilate between those, because this is made up of an anti-strange and an up, and this is made up of an up, up, and a down. So you can't do what the diagrams that I drew before, because none of the quarks annihilate. So the thing that's being exchanged, which at the time when this was first studied was just called the vacuum, nobody knew really what it was. They knew that these processes had the property that they grew and that they were controlled not by the Reggie trajectories that we've just drawn here that go through the particles, but another Reggie trajectory, which is something like that, which was called the Pomeron, named after a Russian physicist called Pomeronchuk. It had the power 1. people speculated, where this crosses an integer, like 2, there should be a particle. Nobody knew what that was. But now that we have QCD, you can draw this diagram clearly another way. So here is the same diagram, I've just distorted it. What is something that has the quantum numbers of the vacuum that can be exchanged here? In QCD, they're gluons. So to go back to Angela's question, there are things which carry flavor quantum numbers, which are like the resonances, and they're the parts which have vacuum quantum numbers, which are related to the gluons and Pomeron exchange. So now the modern representation is that the Pomeron, it's usually drawn with those two lines, is equivalent to gluon exchange. And in fact, that's the most important, the leading Reggie trajectory. It's the highest one. Remember, the scattering region is T negative, so it's the Reggie pole, the dominant one, that tells you S to the highest power would be the one that's the highest up, and the highest one is this Pomeron. So, probably have to write something here, which is that we learned that total cross-sections for any process, including K plus P goes to K plus P, is equal to 1 over S times the imaginary part of the forward elastic amplitude. The 1 over S is a sort of kinematic factor. That was the bit we got from the optical theorem. And now Reggie theory tells us that this is going to be, well, what the minus sign is doing doesn't matter. It's related to crossing properties. It's alpha at t equals 0 minus 1. And the minus 1 comes because of that. And because it's the forward amplitudes, it's at t equals 0. And the leading, there is a theorem, that's the last thing I want to say, from unitarity before we stop, something called the Froissart bound, which says the fastest that total cross-sections are bounded by a logarithm squared of the energy. And that means that the highest Reggie trajectory must be less than or equal to 1, and the Pomeron is exactly equal to 1, or very close to it. So high energy behavior of total cross-sections are dominated by vacuum exchange, vacuum quantum numbers. Now, I realize that was very speedy. It is sort of amazing that some idea from potential scattering of continuing angular momentum to complex values turns out, in the case of relativity, where a relativistic process, where one region and another region are connected, and where the same scattering function describes the process, one complicated analytic function which we can't write down, describes what's going on in the whole plane and enables us to go from one region to another region and connect them to each other. And these dynamics are connected. And as I said, whilst at low energies a process is controlled by resonances, at high energy it's controlled by the exchanges in the cross-channel, and these exchanges are summarized, or most economically, in terms of these Reggie poles, which are the continuation of essentially the resonances in this channel to complex values of angular momentum. It's a bit amazing that that happens, but it's true. And as I said, the hadronic string automatically embodies that. It was the basis of it. Okay, that's probably a good place to take a 5-minute break while we set up, and I'm going to just give the rest on a, really just to pull some basic ideas together, okay? So you can see where the future lies as well as where the past lies, okay? Probably it's better to use the main one, isn't it?